It started. So again, let's go to the page of the Imod model that I want to discuss a little bit. I want to make a small recap, a short recap before passing to the exercise. So let's click on it and let's go to this page. And let me go to the page of the Imod model, sorry, to the section of the Imod model, which follows the linear reservoir. Here it is. Okay, now I want to make, as I said, a brief recap of how it works. I think the recap is useful because it allows us to better understand how we can write a code for the Imod model, because today our purpose is to apply it. To apply it by using rainfall data, evapotranspiration data, and observed river flow data to be used for the sake of comparison between simulation provided by the model and observed data. Now, let me just pass to the graphic blackboard, because I want to make a sketch to help you to understand. So let me go here. Okay, very good. And as I said, let me make a brief recap by first drawing a conceptual scheme. So let me make a drawing of a linear reservoir. This drawing, this scheme in drawing of the model, I call it a conceptual scheme. It's a scheme, a graphical scheme that allows me to focus on the concepts, and the concept is what I want to recall. So let's make a scheme of a linear reservoir, as I said, like this. Okay. Okay, very good. In the linear, how does it work, the linear reservoir? First, let me draw the bottom discharge here. In order to exemplify how it works. And so let me make the bottom discharge here, which is fine in this way. Okay, very good. What it happens here is that you have some rainfall getting into the tank, PT, and then inside the tank you have a volume W, okay, which I can identify here. It's WT at each time step. And at each time step, I have an outflow QT from the bottom, which is okay. This is the linear reservoir. Now, let's try to draw a conceptual scheme of the Imod model. So let me delete this. And but before deleting, let me just remind you that in the linear reservoir, you have this storage WT, which it represents water that is stored into the catchment. It's stored into the soil, etc. And it is assumed that the catchment has a storage capacity which is uniform. It doesn't change over the catchment. With the Imod model, now you remember that you have a storage that is varying, okay? So in different locations of the catchment, you have a different value of the storage. Now, we need to change this conceptual scheme then. This conceptual scheme doesn't apply to the Imod model because I have to visualize in the conceptual scheme of the Imod model that the water storage capacity, it's different. It assumes different values in different locations of the catchment. So let me redraw then the conceptual scheme. So I go back because I'm not interested in the linear reservoir anymore. And let me go to this situation. This is my catchment, but I have to make clear that basically the depth of this tank is not constant, but I have to basically represent my catchment with a series of several tanks, several small ones. So instead of a unique tank, I have to put together a series of tanks with different depth. So let me do that. Let me now visualize here. Let me decompose this tank in several small tanks, and it will take a while to me, but let's make it as quick as possible. Okay, so this is the first tank, and let me make the height of this tank, yeah, in this way. Perfect. Now, second tank. So I start from here, and this second tank has a different depth. Okay, so here I am with the second tank. Third tank. The third tank is, let's make it very small, okay, in terms of depth. Good, very short. And then another one here, and this, let's make it a little bit taller. Here we are. And then another one, a little bit taller again. Okay, and then here we are. Let's make it, let's make another one, a little bit taller again. And here we are. And now let me delete these segments connecting the various tanks. These are separated tanks. Okay, so I have to delete this segment at the base of the tank in order to make clear that these are separated. Okay, perfect. And then I can delete this one. So this is a conceptual representation of my catchment with several tanks with different depth. Okay, now what happens when it rains? It's a little bit more complicated. So I get, let's say, at the first time step, I get a P1. Okay, this is rainfall at the first time step. What happens here? It happens that I get this rainfall. It's accumulated. It's accumulated in each tank. This rainfall falls over the whole catchment. It falls over all the tanks. Okay, so in each tank, I get an accumulation. Let's suppose that this accumulation of water, it's like this one. Okay, let's suppose that we are at this level here. Good. And now let me delete the storage between tanks. Okay, so I get this in each tank, I get this storage, and none tank is filled up according to this representation. So what is this level? This level, I can indicate it with the symbol. Sorry. Good. With the symbol CT. Okay. This is my CT. Let me indicate in this way, C1 precisely. So this is storage into the unsaturated areas. So it's what I called C. C, depending on time, in this case, it's C1. And given that none tank is full, I don't have any outflow, so no QT. Okay. Now let's suppose that I get a second pulse of rain, P2. Okay, and this, sorry, I go back a little bit. Given that I don't have any outflow after the first pulse of rain, this C1, it's equivalent to W1. Good. Now, let's suppose that I get a pulse P2, and after the pulse P2, let's suppose that I get at this level here of CT. Okay, good. This is, let me indicate it here, this is C2. But what happens here? It happens that I have one reservoir, one tank that was saturated. So if you look at the third tank from the left, you see that the value of C2, it's higher than the depth of the tank. So what does this mean? Let me choose a different color. It means that this part of rain here, it's overflowing, meaning that this is a contribution to what? To river flow, to surface runoff. Let me call it, this one, let me call it ER, sorry, ER2 at time step 2, okay? So at time step 2, thanks to the second pulse of rainfall, P2, I get first contribution to surface runoff in red. I call it ER2, and forget about the symbol. The symbol is just to be consistent with the literature, okay? ER2, depending on the time step, which is the second, okay? There is no relationship between the name ER2 and the number 2 with the time step in parentheses. It's just a coincidence, okay? Very good. Now, what happens if, in this case, what happens to the value WT? WT, which is the storage into the catchment, is no more equivalent with the level C2 of the storage in the unsaturated areas. It's not equivalent because the storage is deprived of the contribution of the red rectangle. So basically, in the third tank from the left, you cannot store water anymore, which means that the overall storage into the catchment is deprived of the contribution of that tank. So if I want to make clear what is the overall storage in the catchment, I need to draw a line which is a little bit lower, and let me use another color, not the red one, but let's use, for instance, for storage, let's use the purple color, okay? And let's make it a little bit lower with respect to the C2, okay? This is my storage W2. Again, what is the difference between the light blue line C2 and the purple line W2? The difference is the volume of the rectangle, because in that tank I couldn't store water anymore. So the storage of the whole catchment is deprived of the contribution of the rectangle, which is my river flow. Okay, now let's take another pulse of rain, okay, P3. P3. Good. Now, what happens? Let's suppose that we get to a very high storage into the catchment. And for instance, let's suppose that we get to this level here. We get here, okay? We still have some of the tanks that are still getting water. They are not saturated, but there are many tanks, and let me show them in red, that are saturated and their capacity then exceeded. So these tanks are this one here, and this is the contribution to the surface runoff. Okay, just 1 second. This is my contribution to surface runoff in this tank, which is fine. And then I have this tank here. So let me indicate it. And in this case, I need to go. I am going over this writing, so I need to be a little bit more close here. Here I am. And this is my second contribution to river runoff. And then I have this one here, which is even this one, it's saturated. And let me just indicate it in this way. I need to make breaks in the lines because I don't want to overlap the writings. And this is another contribution. So basically, you have now 3 reservoirs contributing to surface runoff. And let me make clear that this is the level C3, which is the level of water in the unsaturated storages, which is the sum of the 3 rainfall pulses, P1 plus P2 plus P3. And then if I want to show the level in purple of W3, this will be somewhere here. Okay, this is W3. And then we may go on. So the important thing is to understand that the catchment is represented through a series of tanks. We don't know where they are located. We just know their probability distribution. And these tanks have different depth. So as long as they get filled up, they start producing surface runoff. Now, we have to translate this into a code. So what we have to do, basically, is at each time step, as you see, to compute C. To compute C, to compute W, and depending on rainfall, of course, and then to compute this contribution ER2 to the surface runoff. And as long as the event goes forward, we have at each time step to update the value of C, the value of W, and then compute the contribution to the surface runoff. Okay, and keep in mind that we are not depicting here first a couple of things we are not depicting here, and let me make it clear. One, we need to subtract evapotranspiration from storage. Evapotranspiration from storage. Very good. At each time step. So this is something that we don't have to forget, okay? I'm not making this step visible in the drawing because I don't have, you know, space here. This is something that we don't have to forget. 2, we need to consider the contribution to runoff when the catchment, I go writing here, is fully saturated. I try to better explain. You will reach at a certain point with the level of C, you will reach the highest depth of the catchment. So basically at a certain point, let me take the purple line, you will get to this height of C. So in this case, you have CT equal to what? To C max. So when you get at this level, CT equal to C max, what happens? CT reaches its top. Its top. So you get to the top value of CT. And in this case, you will see that for computational reasons, you will need to compute the contribution to the surface runoff. We need, sorry, we need to compute ER in a different way. In a different way. And from a computational point of view, we need to compute it in a different way because you will see that until we are at a level of CT that is lower than Cmax, we can compute ER2 as a function of what? Of CT and WT. This is up to if CT is lower than Cmax. But if we go to a new situation, if CT is equal to Cmax, this is a different situation, then I need to compute a second component, which I call ER1, which is a function of rainfall and Cmax. So you will see that from a computational point of view, I need to compute, to substitute the computation of ER2 with another computation. And I will explain when we look at the code. So this is the conceptual scheme that we have to follow. And now we are ready to write the code. And so let's look at the exercise then. Any questions so far? Let me have a look at the chat if there is something. Let me see. I don't think there is anything here. Very good. And now, if you don't have any question, let me share the screen of the web page. Okay, good. Before I move forward, let me recall the formulas that we need to apply the model. And let me go down here. So I need two formulas. The first is this one. A formula that allows me to compute WT at each time step. Okay, it's computed depending on CT. So once that I compute the value of C, this formula allows me to compute the value of W. And the W, it's, as you may remember, it's maybe equivalent to C or maybe lower than that. Okay, lower because you remember in the conceptual scheme that I have to subtract what cannot be stored in the saturated areas. Now, the second formula that I need is this one. It's a formula that allows me to compute C depending on W. It's the inverse of the previous one. So just keep this two relationship in mind or noted, but we will have the opportunity to look at them again when I introduce the code. Very good. Now, let's also look before we move forward to the formula for computing W max. Good. And let's look at this shape here for probability distribution of the storage over the catchment. And this shape, which is visualized here for a value of beta, which is equal to 2. But basically, this shape tells us that we have at least a very small area in the catchment that is impervious, which means if you look at the probability distribution FC on the vertical axis for a storage C star that is equal to 0, very close to 0, you already have some probability to find some areas, which means that there are in the catchment some very impervious areas. Very few, but there are some, which means that as soon as it starts raining, we start seeing some water into the river. And this is something that you have to keep in mind, depending on the shape that you take for this probability distribution. If you take this shape, which is the shape that we will indeed take in our exercise, you have to expect, given that there are some impervious areas, you have to expect that as soon as it starts raining, you see some water into the river. Okay, but now let's look at the code. So I go back to the main page of the course, and let me click on the exercise. It's here, calibration of the Imod rainfall runoff model, suggested R code. And first, let's look at the data. And this rainfall and evapotranspiration data. This is the same data set that we used for applying the linear reservoir. Okay, perfect. Let me go back and let's look at the river flow data. Same data set that we used for the linear reservoir. Very good. Now let's save them. Okay, so I click with the right and I save them in the desktop. So I save destination with name, and I put them in my desktop. I'm working on Windows now, so it's particularly, I think I am viewing on my screen what you are viewing. So I save it, and now let's do the same for the river flow. Okay, save destination with name. I save it on the desktop. Save. Perfect. Now I have the data, and now I need to start an RStudio, a session of RStudio. I don't remember if I already installed it. If not, you will need to be patient with me. But I think, let me see. I don't remember, really. I need to check. So I don't think it's already there. Just 1 second. I don't think so. So let me download it. Okay. And I don't think so. Okay, let me just give me 2 minutes. Okay, and then I install Okay, download. because as you see, I passed to Windows for teaching because finally I realized that for teaching it's a better solution. For teaching because the use of the graphic blackboard it's easier. 1 second, I am installing it. Let me install it in English so we have the same language. Okay. Okay. And now I need RStudio. So it's RStudio. Okay. It's installing. Now download. Okay, RStudio desktop download. Very good. Here we are. Good. R is installed, which is fine. Let me install RStudio. And then let me launch the installer, and then we can go to see the code, the suggested code, because also for applying the Imod model, there is a suggested code, and we have to be very careful in trying to understand what the code does, the same reasoning that I made for, okay, now it's installing, very good. So let's go here. This is again the web page of our course, and let's look at the R code for resolving the exercise. Good. Now, the first thing that we have to do is to upload the data. Okay, so let's forget about the comments and let's use a scan instruction, which we already know, to upload the rain and evapotranspiration data. This instruction, as I said, it's a scan function. We already know it. We give the instruction to the function to skip the first line because the first line was the heading. Now let's copy this with the right click of the mouse and let's put it in RStudio. Let me see if installation is completed. Yes. Let me start RStudio then. RStudio, it's here. Very good. Now give it 1 second. Here we are. Perfect. Yes. Okay, here we are. And what we have to do first is let me take the fonts a little bit larger. And let me see if I zoom out. Yes, I think I can do this. Very good. Okay, now the font is larger. And let me clear the console. And I need to set the working directory. Set working directory. I choose the directory of the desktop. Open, very good. And let me also open a script file because again, I don't want to copy the instruction in the console. I want to create a script. So new file, RScript. Here we are. And let me save it already. Let me save it in the desktop and let me call it eseimod.r. Save. Very good. Now I can right click and paste in the script the scan instruction. Let's see if it works by giving a run. And you see that if you look at the console, indeed, it read 17,520 items. And this is fine because it's 1 year of hourly data, which means that you have a total, let's go to the console, a total of 24 hours time 365 days times 2, because I have rainfall and evapotranspiration. And you see that indeed the number is what we are expecting. Very good. Now let me clear the console. Okay, now let's go to the second instruction. The second instruction is the scan function for the river flow, for the observed river flow. Very good. Let me go to the code and let's copy the second line. Oh, sorry, the second line is not the scan function of the river flow. This goes later. It's here. Let's take this, okay? Copy. And then I can paste here. Let's make it a run. Let's give it a run. Okay, very good. This is okay. Now, the vector with rain and evapotranspiration, you know, it's a vector. And with two variables, two columns, so I have to transform it into a matrix, because if you look at how it looks, for instance, the first 10 numbers, you see that again, you have a number of rain, a number of evapotranspiration, a number of rain, a number of evapotranspiration. I have to separate them. And the way to separate them, we already know it, because we already did it for the linear reservoir. And just 1 second, I need to cancel this. Okay, so we already did it. We need to transform this vector rain evapo into an array. Let's go back to the code. Okay, here we are, and here it's the instruction to transform a vector into an array. Okay, let's copy it. And let me paste it. So basically, you see that rain evapo is transformed into an array through the array function. And the argument of the function is the vector, which is the same name, meaning that with the array, I will substitute the vector. And the second argument is the dimension. Okay, let's run it. Very good. Now, I have finally created a matrix, and if I visualize the first column and the first 10 rows of the first column, oops, sorry, there is something here. Sorry, this is the code. Let me put it in the console. You see that I have only rainfall. So I have put rainfall in the first column. If I go to the second column and look, in order to recall the previous instruction, I went with the arrow up, okay? Arrow up, I get the previous instruction, and then I go inside and I put the second column. In the second column, I have evapotranspiration. So I succeeded in separating the two variables. Evapotranspiration has the same numbers, the same values. Why? Because evapotranspiration is usually computed at a daily time scale. And therefore, given that the model is running at hourly time scale, we simply split here the daily value in 24 equal parts. Okay, just 1 second. I have a person in the waiting room. Let me admit them. Okay, so So this is why evapotranspiration has the same value. You don't have to be concerned. Rainfall, it's 0 because the first 10 values are no rainfall. Of course, rainfall is intermittent. Okay, now let's go back to the code, because what the code is now suggesting is to rename these variables into two vectors. And this is useful indeed. Instead of using an array with first column for rainfall and second column for evapotranspiration, instead of using an array, let's create two variables called P and EP for rainfall and evapotranspiration. Let's give it a run. Okay. Now, if we go to the console, we can make a plot of P, which is rainfall. And here it's your plot. And we can make a plot of EP. And here the plot, you will see that it's a plot of, it's for 1 year. It's a plot of a sequence of constant values, okay? Because it is computed actually it is computed at the monthly time scale. So for each month you have the same potential evapotranspiration. This is potential evapotranspiration, okay? It's the max evapotranspiration that you get if you have unlimited water in the catchment. Okay, very good. Now we have uploaded our data, which is what we wanted to do. Now let's go back to the code and let's try to, we already uploaded our observed data of river flow, so we skip this because it's already placed in the script. Now let's create this function to apply Imod, and let's put the application of Imod into a function, okay? So a function that allows us to run Imod several times, depending only on the parameters. Okay, so let me create this function, and let me also copy the curly bracket. I go to the script, and here we are. Okay, and so this is my new function. Again, I could have put the instructions to run Imod in sequence without creating a function, but in this case, you know, it would be more complicated for me if I had to run it several times. If you plan to launch, to run a sequence of instructions several times, it's better if you use, if you create a function. And look, I am indeed planning to run Imod several times because I need to calibrate the parameters. And calibration, you already know that needs a trial and error procedure. Calibration needs to run the model several times. Okay, 1 second. Okay, good. So now we have to start our instructions to run R. R is to be, sorry, to run Imod. Imod is to be executed by repeating at each time step what we highlighted, visualized in the conceptual scheme. At each time step, I have to look at rainfall, compute the values of C, W, and the contributions to the surface runoff, ER. ER1 and ER2. ER1 is after catchment saturation, ER2 is before catchment saturation. if you remember the scheme that we plotted out, the scheme tells us that at each time step, at each hour, we have to look at rainfall, compute CT, compute WT, and compute the surface runoff. Good. So I need a cycle, okay? But before making the cycle, I need also to initialize all the variables that I need. So let me look at the code in the website. You see that here there is the initialization of a series of variables. Let's copy all of them. Okay. I copy all of them. Not all the initialization. Let's stop here for now. Copy. And let me go to the script. Paste. And let's look at each single variable that I am now defining. Area B is the catchment area in square meters. So if you look at our text of the exercise, the catchment area is 1214 square kilometers, which means 1214 plus 6 zeros square meters. Very good. The second variable that we define is the time step. It's 3600 seconds. Very good. Now, we define also the number of time step. So in the line before, we defined the extension of the time step. Now we define the number of time steps. It's, as we already discussed, it's 8,760. Is 24 hours per day times 365 days. In a year, you get that number, 8760 hours. Now, let me also define the initial value for the river flow. I'm not starting from 0. Let's say that Imod gives us the opportunity to start from a given value of river flow, and let's start from 15. Now, let me define a conversion factor. You will see that later on, I will need a conversion factor in order to take into account that rainfall is given in millimeters per hour, and then I have to transform it in meters. So I am dividing by 1000 in this line. Again, rainfall is in millimeters per hour. I need to express it in millimeters per hour, in millimeters per second. And therefore, I need to divide again rainfall by the time step, which is what you see precisely in the selected line here, the code. And then, in order to get the volume of rainfall per unit time, because you remember Imod wants the volume of rainfall per unit time, I need to compute the rainfall. I need to multiply the rainfall by the area of the catchment. So this is the purpose of this conversion factor, which I will use later, okay? Because I will need to transform rainfall into river flow. And therefore, later on, I need this conversion factor. Good. Let's move forward with the definition of the parameters. I have to initialize them. The parameters, you see the argument of the function are given through a vector called PAR. For the sake of simplicity, I want, and for identifying the meaning of each parameter into the vector, for getting this identification, I prefer to assign to each parameter a variable. Cmax, which is the parameter in the first position of the vector PAR, beta, second parameter in the vector PAR, alpha, third parameter, K-slow. You remember that in Imod, I have a linear reservoir to route the low flow. And this is characterized by, this linear reservoir is characterized by a constant K slow. It's the fourth parameter. K quick. You remember that again in Imod, we have the quick river flow that is routed through a series of 3 reservoirs, which is the fifth parameters. I just want to give you a reminder of this. Let me go to my website, and which is here. Let's look at Imod. There is a scheme, you may remember. Here it is. So you see that the contribution of the surface runoff, it's split through a parameter alpha, which is the third in the vector PAR, in 2 components. One slow component, look at the bottom, with a routing realized through a linear reservoir with the parameter Ks, K slow. And then I have a quick component which is routed through a series of 3 linear reservoirs. Okay, this is why I have 5 parameters. Good. Let's go back to the code. And now I have to initialize variables. Let me copy this comment. Copy. I go to RStudio. Let me go here. Initialization of variables. I need to initialize several variables that I will use later on. And if you look at the code, there are a series of variables that I need to define. And I propose that we skip this part for now, because if I initialize variables before explaining to you what is their meaning, you cannot understand what is the meaning of these variables now. So I suggest that this series of lines is skipped. And then let's go to the computation loop. And then we define in the computation loop variables, and then we go back to defining in the code their variable, their value. Okay, so let's skip this part, and we will do these lines one by one later. Okay, now let's look at the computation loop. Let's copy this instruction and in the code. Now we are starting the computation loop here, and let's set the initial time step of simulation to 1. Okay, why I am including this line? Because later on, for validation, I may need to run the simulation starting after time step 1, later. Okay, for now, let's put this value, which means that I'm starting from time step 1, and then I can start the computational cycle. Let me look at the code. You see a 4 here. It's a cycle. Let's copy it and let's paste it. Okay. 4 I in 1 I in SK, which is 1 for now, 2 and delta t. This is my computational cycle. It goes through each time step. Okay, fine. What do we have to do at each time step? Now let's skip the first line and let's go to the second. The first line, we will do it later, okay? The second is the computation of C1. Perfect. Depending on what? Depending on W. So let me show you the formula that I'm using to compute C1. Okay, So C1 is, again, the value of CT at the first time step. Let me show you again the formula that I use here, okay, in the blue line. The formula, I go to the web page and let me check. I think I have another one open. No, it's correct. The formula is this one. Sorry. This is the formula that I need to use. This formula gives to me the value of C depending on the value of W. Good. Let me go back to the code. And let me copy this formula. Okay, copy. Now let me go to RStudio. Here it is. Again, the formula that I copied here is the same that you see here. Okay, if you make a check, it's the same formula. But on the other hand, I need the value of W. So here, I will need to put a relationship W equal to something. Okay, let's wait before putting this relationship. Let's just note now that I need a computation of W here. Okay. Second thing, I am using these variables inside a for cycle. So here, for sure, in the initialization of variables, it's much better if I write C1 equals 0. Okay. So this is one of the variables that I need to initialize. Okay, but now let me just note that we just computed C1. Okay, good. Now, what happens? It rains. I get some rain. So from C1, which is the value at the beginning of the first time step, if I add rainfall, I compute another value of C. Let's call it C2 because it goes to the subsequent time step. Okay. And the C2, in order to compute it, I have to take C1 and add rainfall. So let me go to the code. So the code is here. C2. Okay, good. Let me copy it and then let me comment on it. Copy. I put it here. So C2, it's equal to what? Look, C1 plus PI, which means C1 plus rainfall at the current time step. Good. On the other hand, I have to make sure that in doing so, the value of C doesn't exceed C max, because C max is the max value that C can assume. So what is the way to make sure that C1, C2 doesn't exceed C max? The way is to put this condition. So C2 is equal to the minimum value between C1 plus rainfall and C max. In this way, I am putting in the same line two instructions. I compute C2 and I check that C2 is not greater than C max. If it is, then C2 is equated to C max. Questions? Let me check if you have any. Okay. Now, Let me say one thing. I go back to the code. Let's suppose that C2, after computation, after summing rainfall to C1, let's suppose that C2 becomes greater than Cmax. So this condition tells me that I have to equate it to Cmax. On the other hand, if this happens, it means that I have to compute a contribution to the surface runoff, because if C2 is greater than Cmax, it means that part of the rainfall, Pi, could not be absorbed by the catchment. And therefore, this rainfall, this excess rainfall with respect to saturation of the whole catchment, gives a first contribution to surface runoff. So here I have to put a computation for ER1, first contribution to surface runoff. And now you understand why I call it ER1, first contribution. It is a contribution that could be 0 if the catchment doesn't get to saturation, but if the catchment indeed gets to saturation, then it's different from 0. So ER1, here it is. And let's copy it and paste it, okay? And I need to do it like this. ER1 of I. So what is this contribution? It's equivalent to the max between 0, so cannot be lower than 0, of course. We are talking about flow, cannot be negative. It's the max between 0 and Pi minus Cmax plus C1. So you see that if indeed C2, which is equal to C1 plus Pi, exceeds Cmax, which means that Pi minus Cmax plus C1 is greater than 0, then if the catchment is saturated, you have a value of ER1 that is different from 0. Okay. This is what allows us to compute this first contribution to runoff that only occurs if the catchment is fully saturated, okay? If ER1 is 0, it means that the catchment is not fully saturated. Okay, let's move forward then. Now we have to compute W. A new value of W. Let me copy this. This is a new value because remember that we needed a W at the beginning to start, at the beginning of the cycle. This is a new value of W after rainfall. And this new value is computed depending on the value of C2. You see C2 here. C2, which was updated here. And what is the relationship that I use to compute W? Let me go back to my website and I show it to you. Sorry. Here. Let me step back to the page, and this is the relationship. And look at the right-hand side in the far right. WT is equivalent to the relationship that you see on the screen now, which is translated into this instruction. Now I go back to RStudio, okay? Here it is, W2. So this is the new W, again, after rainfall. Look, if the catchment got to saturation, this W2 would be equivalent to W max. Perfect. Now it's time to subtract evapotranspiration from W2. This is basically the value of the catchment storage after rainfall. Now, before closing the computation, we need again to subtract evapotranspiration. Okay. And here we go. First, sorry, before subtracting evapotranspiration, let me compute the second contribution to surface runoff, okay? Because we compute it before subtracting evapotranspiration. And let me copy it. And this second contribution, how we can compute it? Okay, let's see. It is computed in this way. We compute the difference between C2 and C1, which is rainfall, okay? So rainfall minus what? Minus the difference in storage, W2 minus W1. W1, it's the W that I put up there. Let me put in the first line of the fourth cycle, let me call the variable W, W1. So I have two storages, one before rainfall and the other one after rainfall, okay? And then over the catchment, I have rainfall. Now, it's clear that if the difference between the two storages, W1 and W2, is equal to rainfall, it means that all the rainfall was stored. But if the difference between the two storages, W2 minus W1, is lower than rainfall, it means that part of the rainfall was not stored. So by computing this difference, which is rainfall minus W2 minus W1, if this difference is positive, it means that there is a contribution of rainfall that was not stored and therefore produces the surface runoff. This is the surface runoff that comes from the fact that the catchment is not fully saturated, but some part of the catchments are. They are saturated and therefore they cannot store any more water. Okay? And this is the second contribution. Good. Now it's time to compute evapotranspiration. Here, and here you have the computation of the actual evapotranspiration. And this formula here, let me copy it and I paste it in RStudio, and then I'll show you from where it comes from. So let me compute it, let me put it in RStudio. And now let me go back to my website. I want to show you the shape of this relationship that is translated here into a code. Okay, let me go back to the website here, and here is the relationship. Here it is. Okay, here the potential evapotranspiration EP that you see on the right-hand side, it's known from the input data. It's the variable EP that I loaded into my code. And then there is the quantity between round parentheses, which is a linear relationship. We already commented it. And this is translated into the instruction that now I show you back in RStudio. Good. Perfect. Now we need to subtract this E. Look at the last instruction, this E now selected. We need to subtract it from W, the storage into the catchment. We need to subtract it from W2. It's the last storage that we computed. Very good. But we have to make sure that by subtracting evapotranspiration, the storage doesn't become negative, which wouldn't be meaningful. And therefore, I make the subtraction with a condition. Let me go to the code. here, and here there is the computation of the new W2. Copy. We are, and you see that the new W2 is equal to W2 minus E, with the condition that it cannot become negative. Good. Okay. Now, let's, at this stage, compute the total contribution of surface runoff. I am just summing year 1 plus year 2. I go here. It seems that I didn't copy it. 1 second. Okay, here we are. Now, what I just computed is the total contribution to surface runoff, which comes from the partially saturated catchment and from maybe the fully saturated catchment. So this total contribution now is to be split into components, and you may remember, let me go back to the website and the sketch here. Now we have to, this is our ER. You see that it comes from the sum of year 1 plus year 2. And then it has to be split into two components through the parameter alpha. So let's go to the code here. And then you see that I am subdividing ER into contribution quick and slow. Okay, let's copy it. Oops, sorry. Quick and slow. Let's copy it. Let's go to the code. Here we are. And now these two contributions, quick and slow, need to be routed. We need to route them. The U quick is to be routed through 3 linear reservoirs. The U slow needs to be routed through a single linear reservoir. Now, you know how to apply a linear reservoir or a sequence of 3. It's not a problem. We already applied a numerical scheme in a previous exercise to run a linear reservoir. In this case, I would like to make the numerical scheme more self-contained. And there is a way, indeed, to make it simpler with respect to what we did in our exercise. Our exercise adopted a code that had the advantage of being very clear. I mean, very clear. Let's say that it was the clearest possible way to write it. Now I am proposing to you a different numerical scheme, because you may remember that several different numerical schemes are possible. I would like to propose you a second one, which is simpler. It's self-contained, but of course we would need to explain how it is derived. And indeed, in your code, now I will go back to the code on the website, there is a theoretical proof of how it is derived. It is commented out. Let me go to the code, okay? You see that there is now slow flow, and then there is this explanation. The linear reservoir is resolved with the following relationships. Okay, this explanation gives to you the reason why I can simply write the routing through the linear reservoir through this instruction and this one. So you see that these two lines allows me to start from U slow and K slow and compute Q slow. And look, there is also a previous value of W's law that it is used in this relationship, which is what we defined at the beginning. Now, I suggest that we don't now focus on this explanation of how the linear reservoir is applied. I suggest that we just copy and paste this and take it for granted. If you are interested, just look at the commented lines. There is a very simple explanation of why we can write the linear reservoir in this way, which is interesting because it shows to you that by adopting a different numerical scheme, you can simplify things, but I leave this to your personal study if you are interested, okay? Now, for the sake of applying Imod, let's copy all of this and paste it into the script. Okay, and you see that we computed then Q's law. Depending on, again, K's law, which is a parameter, US law, which is the runoff computed here, and depending on a previous value of W's law. And where do we define it? Let me go back. I still have to define it, sorry, because it is in the chapter of the initialization of variables, which I decided to postpone. So I will need to define it here. Very good. And now we have a first contribution to the river flow, which is a first contribution to our final result. We still have one more thing to do, which is the routing of the quick flow. Let me go back to the code. And here it is, quick flow. Again, it is a sequence of 3 linear reservoirs. So we introduce another for cycle, which applies for 3 times the same routing through the linear reservoir. We copy this, we paste this here. And then you see here that we computed U quick, okay, which is the second contribution to the river flow. Now we just need to compute the total contribution of the river flow. And then we can pause our for cycle. Good. So we completed our computation. Now we just have to close the function and then we can take a break, okay? Just save the script once in a while. And let me just put this here. Okay. Yeah. And now let me close the function. And for closing the function, let me draw a plot. And the plot is a plot of the simulated river flow. You see plot QT, which is the total flow. But also I put there the observed river flow. You see that there is a lines and instruction lines QOS, which means that I want to draw a superimposition of observed plus simulated river flow. And then I can return, let's skip the commented lines. I can return the sum of squares, observed minus simulated squared. And by returning the sum of square, I am returning an objective function. So let me do this, and then I can close the whole function. Good. Now, let's try to, at this stage, there is one thing that we are missing, which is the definition of the variables. So before making the break, let me go back. For instance, first of all, at the fourth cycle, we had to define W1. What is W1 at each cycle? It's the volume stored in the catchment at the beginning of each time step. Now, we need to set it equal to the volume stored in the catchment at the end of the previous time step. So here, what we have to do is to write W1 equal W2, because W2 is what we compute at the end of the time step. And then when we go to the next cycle, at the beginning of the next time step, we need to start with the same value of storage. The value at the end of the previous time step is set as the value at the beginning of the new time step, of the next time step. Very good. And then we have to initialize these variables. All the variables that we used, W1, W2, uquick, uquick, uslow, etc. We need to define all of them. In some cases, we need to define them because they are vectors. In other cases, they are not vectors, so we could avoid defining them. But for the sake of clarity, it's better if we define everything. So let's go back to the code to make it simpler, and let's take all the variables. Here they are. W2 equals 0, C1 equals 0. W slow, do you remember that we needed to define it? We can define it in order to give, at the first time step, the initial value of the river flow that we planned. We set it here. Qi equal 15. This is the initial value that we want for the river flow. So this means that W slow, instead of being set to 0, you need to set it to this expression here. Sorry, this one. And here there are all the variables that we need to define. So let's copy them. You see here 1, here 2, ER, E, QT, everything is to be defined. Otherwise, if we don't define vectors, we get an error. So let's go here and let's do like this. Good. Now we can try to upload this function. Let's select it. Let's make a selection of the whole function. And let's run it and see if it goes. Yes, you see that it was pasted in the console with no error. I could have also, instead of running, it would be better to make it source, which is okay. Okay. Very good. Now, let's make a break. Before making the break, what we need to do in the next hour is to run it. We are ready to run it. But before running it, let's take a break. And do you have any question before we break for 15 minutes? Let me go here and let's, yeah, do like this. Okay, no questions. So let's meet again at 11:05. Thank you. So let me just check if everybody's here. Yes. Okay. So where are we? We are now in, let me just share the screen. We are now with this code, which was already uploaded in the form of a function. Now let me go to the console, because at this stage we need to focus on the console. So I am restricting the window of the script and focusing on the console. Let me clear it. First of all, if you write on the console Imod, you see the function that we already uploaded. And now everything is ready to run the model. What we need to do, first, keep in mind that what this function is doing. So let's look at its body in the script. I go to the beginning, and just keep in mind that the function is using input data called with the variable p, which was already defined here. It's using evapotranspiration data potential, which is called EP, already defined here. And it's using the function observed river flows for the sake of comparison and for computing the objective function least squares. And observed river flows, it's uploaded here. So, I mean, everything is ready. And what we have to do is to give to the function as argument the parameter vector. Now let's try, and let's try to run this function. What I am expecting is to get back a plot with observed versus simulated river flows, and I'm expecting to get back the sum of squares objective function. Okay, good. Now, let me clear the console and let's try to run it. Imod, I need to give the parameters. The parameters, let me give trial values. Keep in mind that if I give very wrong parameters, then it may be that the function it doesn't work. It gives an error. Let's see what happens. So let's try to give the 5 parameters: 100 for Cmax. Let's give 1 for beta. Let's give 0.5 for alpha, and let's give for k slow and k quick. Let me give something like I don't know. Let's say 30,000 and 3,000. I'm just guessing. Let's see if it works. Keep in mind that it may give an error because for certain maybe values of parameters it may happen. Let's see. Okay, we got an output. The output is what you see in the graph, and you see that the simulated river flow in red is something really not really meaningful, which is fine. I mean, and you see on the screen it's fine because I just guessed the values of the parameters. And if you look at the screen, this is the value 5 million something of the least square of the sum of squares of objective function. Let's try to reduce the values of k by an order of magnitude, and let's see what happens. Okay, we start seeing something up and down, which is fine. And let me now try to reduce another order of magnitude k. Oh, we start seeing something which is okay. And you see that the sum of squares went down to 1 million. We started from 5 millions, and this is now to 1 million. Let me just say that if you look at the simulation and you compare with what we found with the linear reservoir, this is much better. And let me just note that at the beginning, I set a value of an initial value of Qt which is, I mean, it's not really, I should set an higher value, but we can forget about the initial value because it's something that we can forget for now. So I don't think we can do much better by trial and error, but let me try to put 10 instead of 100 for Cmax, and you see that we get now a slightly higher simulated hydrograph. The sum of squares, it's not bad. Let me try to do this. No, this is not better. I'm just trying, you know, and let's try to get back to this, and let me try with 0.1 for alpha. No, not really good. Let me see 0.9 for alpha. This is much higher in terms of peaks, but it's better for the low flow, but not for the peaks. But I mean, we are starting to see something really meaningful. What I don't understand really, I think there is a mistake in the initial value because it should be 15 and it's not 15. So I don't know why. I should try to have a look at, let me look at the code. And let me try to understand why the initial value, because you see the initial value should be 15, but let me just check. Okay. W slow is equal to, okay. Let me just check. So QI, W slow. Okay, let me check here. In the linear reservoir. Okay. Q slow. I need to, it's not obvious because here it should get to, let me see, W slow. Okay, but W slow, it's W slow. I think probably the reason may be here in let me see here. I am not sure. Let me try to check if I put 1 over here. I'm not really sure. I'm trying to see, I'm changing the code to see if there is a mistake here, which may be because yeah, I think probably there should be written 1 divided by K's law here, but let me see if it is correct. And what I need to do is to source everything. Okay, good. And now let me try to run again the function. I go to the console. Here, let's see. Okay, this is perfect. You see that I adjusted now the initial flow, which is now starting from 15. There was a mistake in the code. I need to check out on the website. Now, let's put, given that the initial value should be around 50, let's put as QI in the code. I'm working on the code 50, okay? Let me source it, okay? And let's go here now. Perfect. Now you see that I get the initial value from 50. Okay, very good. I think this is perfect. I just need to remember to modify the initial value on the website, but this is not a big problem. Okay, good. Now, what's the matter here? The matter is that now, with trial and error, I doubt that we can do more. But still, we could of course, there could be a value, a combination of the parameters that leads to a better objective function in terms of sum of squares. So the question now is, how could we automatically make the search? So how could we pass to automatic calibration? Okay, and by noticing that this value of parameter vector that I see here, look at the console, I am highlighting the parameter vector 10, 1, 0.9, and 330. So the question is, how can we automatically search for a better parameter vector? And in terms of what better? Better in terms of sum of squares. We mentioned that we could use automatic calibration. And then the question is, it's possible in R to use automatic calibration? Yes, the answer is yes. And the answer is yes, because in R we have functions, and we have several of them that can look automatically for the minimum value of the least squares objective function. So let's clear the console and let's look at our code in the website. If you go to the bottom, you see that there is a section called calibration of parameters on the whole time series. Okay, and there is here an instruction, a suggested instruction. Let's copy it and let's put it in the console, not in the script, okay? Because this is something that is for the console. And let me go back to change the initial values of the parameters, because you see that, let's look at this function. It's called optim, okay? Selecting it, optim. What is the argument of this function? First of all, the result is assigned to a variable, which is called PR1. This is an arbitrary variable, and I need to assign the result to a variable because the function gives back not only the best parameter values, but it also gives back informations on the search that Optim did. So it's better to assign it to a variable, PR1 in this case. Now, the argument of Optim are the value, the initial parameter value, and let me use those which we found in the previous trial and error run. If I well remember, it was something like 30. I don't remember anymore. 330, something like this, or 3300. Okay, and now the second argument is the name of the function to be minimized, Imod. Good. Forget about this third argument, which is the search algorithm to be used. We don't go into these details, but here we have, sorry, it was 10, not 100. We have the lower and upper values for the parameters. So let's give the lower to 0.1, this is fine, 0.1, and then let's, okay, I think this is fine, and then let's look for the upper values, 400, 10, I think it is okay, 0.9, I would say, I would put here 1, and as upper values, I would put something different from here. Let me, not 30, but let me give 100 and 1000. Okay, let's see what happens. Okay, let's make a run of this. It's running, and there is a mistake because we need to change. We need to change of the sum of the upper and lower values for the parameters. So let me see. let's put something like, I don't remember what was. Okay, let's put something like here. I really don't like the fact that, let me see. Let's run it again. I will get another mistake probably, yes. Let me see. I don't like the fact that it splits the input into lines. So I wanna, no, again, input into line. Let me clear the console, thank you. Now, okay, so lower and upper, let me see. 0.1, I would say. Okay, let's try to run it as suggested in the code. Still, we are getting a mistake because I don't really like the fact that it's split into lines. Let me just copy it line by line. Good. And then let me copy this one. This way, let's see if it works. No. You know, why are we getting this mistake? The problem is that it's the objective function gives back infinite values for the sum of squares. So this is a bit of a problem that we have to resolve by changing the initial values of the parameters. And let me try if I do like this. So 1, 1. I need to converge to the best, to a good solution. So let me try to put here 1000 and 1000. This is probably still too. Now it is moving forward, and you see on the graph that at each trial we see the result. So it looks like now it is moving forward and computing, which means that probably this combination of initial value was okay, and it's already finished. So let's look at the results. Okay, so PR1. Probably, let me clear the console because I'm not sure. I think it is a long. Okay, let's see what gives back. It gives back the parameter values, the value of the objective function, but it's 2 million, which I think it is a bit too, it's not perfect. And then the message convergence 0, which means that it was successful. Now, if you look at the result in the graph, you see that it was better what we found with the trial and error. Why? Because we need to reduce the tolerance. What is the tolerance? The tolerance is the condition to stop the algorithm. And the condition, if you give a strict tolerance, the algorithm continues searching until the strict condition is met. If you put a very relaxed condition, the algorithm makes only a few trials. So I think we have to suggest the algorithm to make more trials. And let's then try to put, instead of here, you see, one E15, let's put 1 E10. What happens, okay? So you see that the algorithm is moving forward. It is quite slow because we are asking the algorithm to make the plot every time. And then it becomes a bit slow. But you see that now it's keeping searching because I gave a tolerance that is lower. And you see that now it is converging very slowly to the best solution. Now, the problem is that if your tolerance is too strict, it keeps searching for a long time, which is a problem. But now you see that it finished. So let's look at the result, PR1. And you see that we got to an objective function of 500,000, which is much better than what we got with the trial and error. And indeed, if you look at the graph, the simulation is very good. Okay. And so what, let me just now try with even more reduced tolerance. What I am expecting if I put 1E8, I am expecting slower convergence. So I am expecting that the algorithm keeps searching for a longer time, and then I am expecting a value of the objective function, the final value, which is a bit lower than 600,000. Let's see how long it takes to get to convergence. You know that it is trying, you see that it is trying to refining, even if, you know, it's, the refinements are very small at this stage. You see that from trial to trial, there are only minor changes. If you look at the graph, you see that it's almost the same. So this means that probably, you know, we exaggerated a little bit with the tolerance. So the message, while we wait for the routine to complete the computation, the message is in each package like MATLAB, R, and even in Excel, you have automatic search algorithm. Usually you need to specify what is the function to be minimized. In our case, it's Imod. You need to specify the initial value for the parameters, and some of them, like this one, want upper and lower boundaries for the parameters. You see, it has completed. Let's look at the result. The result is still, in terms of the value of the objective function, it's not changed much. And let's see the parameters. Unfortunately, I see that here, this is an important thing to note here. If you look at the first parameter, it's 400, which is unchanged with respect to the initial value. Why it didn't change? Because the parameter is colliding with the upper boundary. So it means that we need to give an upper boundary that is much higher, because otherwise, every time that with an optimization, we get one parameter that collapses either against the lower or the upper bound, this means that you need to expand this lower and upper value. And here we have, I think, two parameters which are collapsing. The other one is 0.1. For the other parameters, we see that it's okay. And so let's try to run again the optimization. And what we need to do is to give an higher upper value here. We need to give here a lower value. And I think here we can reduce probably the upper limit. Let's give, I don't remember what was the result, was 70-40. So I think here we can give 100, 100. Let's see what happens. Let's make another search, because I think we may get an improvement now. Because, as I said, I am expecting that by giving more flexibility to the parameter values for those parameters who were collapsing, against the limit, we can get something more, something better. Let's see. Now it's moving forward. You see the graph is still changing quite significantly from one trial to the next one. And now it's converging. You see that its changes are very limited. And let's see, first of all, if we improved in the sum of squares, and let's see whether we have other parameter collapsing against the limits. Remember, if it takes too long to converge, what you could do is to remove the instruction to draw the graph, and then it would improve dramatically the computational time, because drawing the graph, it takes time. And then if it takes too long, you could change the convergence, because I think we are using a convergence that now it's too strict. Now you see that the graph is stabilized. Only minor changes are seen from a trial to the next one. And let's see the final result. But overall, I tell you, in terms of array for runoff simulation for hourly data, this is very good. Usually you don't get these good performances. And I anticipate that once that we completed this one, I think it would be worth trying what happens with a different objective function, and we can do that. Just 1 second, still converging. And remember that if you get stuck in terms of the algorithm not converging, like it seems that it's happening now, you could interrupt the routine and change the convergence factor. And this is something that I would do anyway if I had to make another subsequent computation. Let's see if we can get to the result. Or otherwise I can stop it. But while we wait for the convergence to be reached, let me look at the code and change the objective function, because this is what I anticipated to you, what I would like to do next, to substitute the sum of squares with the sum of the absolute errors. And this would change the results, of course. So now, here, instead of returning the sum of the square of the difference between observed and simulated, let's remove the square here, and let's put here ABS, absolute. Should work. Let me look at the parentheses, if they are okay. Yes, it looks like they are okay. So let me save the script and let me look at the results now of the convergence. You see that if you look at the console, the algorithm converged. Let's look at the results. First, the parameters. Now you see that still there is one parameter that is converging to 0. I would say that in this case, we can keep the result as it is. And this parameter, which is alpha, it means that the alpha close to 0 means that the model doesn't need to split the runoff in two components. It is just one component is enough, which is okay. I mean, this is something that we can accept. And here there is a value of the objective function which is slightly improved. Now, okay, let's look at the new objective function and see what happens. First of all, we need to source the code because we changed it. Now the code is sourced. Let me clear the console and let me rerun the search. Keep in mind that what is changed here is just the objective function. So for the parameter values, we can keep the same limits. And let's see now if the parameters change their value. And one thing could need to be changed, which is the convergence, because the objective function is now much lower in terms of value because it's not squared, the error is not squared, and therefore maybe that we need to reduce the condition to convergence. But let's try to make an attempt without changing it for now, okay? So let's run it. And let's see if it works without any error, first of all. It looks like it is working well. And what I am expecting, it's a lower precision in the peaks, a higher precision in the low flows. First, let me say that the convergence seems to be okay. And in fact, if you look at the peaks, you see that some of them are overestimated. This didn't happen before. And the reason is precisely the objective function, which is changed. And it is in particular the peak after the Howard 2000, which is overestimated. This, as I said, didn't happen before. But otherwise, there are no big differences, I would say. The convergence is still, I think we could change it. In order to speed up the process, let me just, so I show you how to stop the routine. If you go to the console to stop the routine, you have to write Control-C. It doesn't work. Let's see. Okay, so let's try to press stop. And I hope that, okay, perfect. So let me run it again. I pressed the stop to stop the convergence, to stop the search. I just pressed with the mouse on stop here in the upper right corner. Now I am expecting a faster convergence. Let's see. Let's wait a little bit. Okay, so in any case, with this exercise, we learned how to run the model and calibrate the parameters. So basically what we learned is also how to assess the goodness of the fit of the calibration by looking at the parameter values. Now it stopped. Let's see PR1. Let's see the parameter values. And you see that now none parameter is collapsing, which means that indeed the model needs two components for routing. And I think the reason is that in order to focus on the low flows, also the model needs indeed to rely on the two components. Just 1 second, because I didn't turn the phone off. Very good. And so that's it. Okay. Of course, we could try to, let me just clear the console. Let me try to, instead of taking the absolute values of this objective function, we could take the sum of the absolute values to the power of 0.5, which should give even more weight to the lower flows. Let me source it, let me save it, source it. Yeah, there is something which is not okay here, and yeah, correct. I am missing a parenthesis. So let me make, okay, here to the power of 0.5. And then I need a parenthesis here. Let's see if it works now. Let me source it. Yes. And let me clear the console and let's try to run it again. Let's see what happens. You see that the peaks are overestimated, but the low flows are better reproduced. Let's see the convergence. You see the peaks overestimated. It's clear the difference between two different objective functions. If you are interested in the low flows, this is probably a much better simulation. It takes a long time to converge. And but the difference, it looks clear. Okay, and let's let it to run. And I think it's now probably converging. Okay, that's fine. So I think we can stop here for today, and because this basically closes our discussion on rainfall runoff modeling, and then closes our discussion on deductive assessment of water resources availability for surface flows. Now, the next lecture, which will be careful, not next Thursday, and let me go back to our website. So let's look at the calendar. Now we are March 29. We will see each other Thursday, April 8th, because there is the Easter break. So in the next lecture, we will focus on models, groundwater models, but our focus will be fairly limited. And then we will pass to something more technical in terms of design. Okay, let's look at the parameters here. You see that alpha is keeps increasing. So if I want to give priority to the low flows, then I get a higher value of alpha, which is something that I am expecting. Okay, students, questions with the awareness that, you know, today was, yeah, an exercise that I guess it was not very easy to follow. Questions? I am now sharing the screen. I am stopping the recording.